Hey guys, good morning all. Give me a yes in the chat if you guys are able to hear me. Quickly give me a yes in the chat if you guys are able to hear me. Very less turnaround today. What's the reason for that? Only 6 of you have joined. Sunday. I mean, we usually have classes on Saturday, Sunday, but decent number of people join. Maybe it's a long weekend or something. I'm not sure if it's a holiday in India and people have left for something. That can be one of the reasons. Anyhow, no, it's not a long weekend. But we have classes on Sunday. This is not the first time we are having classes on Sunday. We always have on Saturday, Sundays. Anyhow, let's start with this. So today we are going to start a very important topic, which is graphs, which is also the last topic of our DSA. But prior to moving to graph, let's start with what you have completed yesterday. And in addition, I also have the syllabus of graphs, which we are going to see. But anyhow, let's go with the quick revision, what you have done so far. No break, so they are taking break. You guys will have break. Like after graphs, you will have 2-3 weeks of break for system design. And if you guys need break, if you're feeling burnout, feel free to message in the group, right? Feel free to message in the group. There's nothing like you cannot have break. Anyhow, let's come to this first. So in the last class, we were discussing some good trees questions. I think majority of the good tree question we have discussed. So we started with extra interview questions, which are important, which includes view, top view, left view, down view, right view, zigzag traversal, and LCA. LCA, we have not done it. LCA we're going to do right now. Then we'll move to the graphs question. Okay. So very first part, views are sometimes asked in interview. Not sometimes, especially for intern roles, or I would say SD1 roles, they are usually asked. Senior developer roles, I haven't seen somebody asking views. They can ask zigzag order traversal, definition of BFS, modification of DFS. These kind of questions are usual for sure. Anyhow, let's understand if such kind of question comes, how do we handle this? Left view, right view, top and bottom view. So left and right, pretty much the same thing. Top and bottom, pretty much the same template. Only if a few conditions will change in the template. Let's see the first question. Lead code 199, binary tree, right side view. What do you mean by right side view? Right side view means if you're having a tree like this, 1, 2, 3, 4, 5, 6, 7. If you're standing on the right side, how will the tree look to you? So if you're standing on the right side, there will be some overshadows part. Overshadow means this one does not have anything else to shadow, so this one will be visible. If you're standing here on the right side, and if you look at 3, you will not be able to see the 2 because they fall in the same line of sight. Similarly, if you're standing at here, and if you look at here, you will not be able to see 6, 5, and 4 because they fall in the same line of sight. That is why you'll be able to visit 1, 3, and 7. If it goes for this, you will see 1, 2, and 4. That is how for the skew tree also. Now coming to this is what I need to do is I need to find the right view of a binary tree. Now, BFS is easy to do, right? BFS solution, I believe most of you would have done. So I'm not going for the BFS. I'm trying to go for a DFS. Okay. Guys, BFS is super easy here. There's nothing to add. You go to visit any node, just go to the right, recur right, print right, that's all. DFS is something which I've written the code for. Now, what is the DFS code? If I talk about normal DFS, we have 3 DFS: in order, pre-order, post-order. In any of these DFS code, in order, pre-order, post-order, there is no order where I'm covering the right first. This is root, this is not the right. So this right is done at the end, this right is done at the end, this right is done at the middle. But there is no order in which I have to do right at the beginning. So any of these DFS will not give me the solution. So I have to modify the solution. So what should be the approach? If I want to solve it by DFS, approach should be, I want to modify DFS to travel right node first, then I will go for the left node. Okay. And the moment I go to the right node, I'll stop there. I mean, not stop there, I will just print there or add it to my answer, whatever it is. Also, I need to make sure that every level of DFS I'm doing, only one node is visited. That is the rightmost node. That we have handled in the first condition. And third part is it should be extensible. So if I have to do the left view, I have to do minimum number of code changes. And always make your code as extensible as possible. Now let's move to the code part. Intuition is each depth of the tree is going to select one node and current depth is going to increase by 1 for each depth. And that should be equal to the list size. This part, line number 154, it is making sure that at every node, every depth you are visiting, you're visiting only the one children. Approach is this, as we just discussed. Let's move to the code part. In the code part, what you are doing, you're just calling a right view DFS. In the right view DFS, this is the base case you check. Need to make sure that every level of DFS, only one node is visited. That is why current depth equal to result.size. You're always incrementing the current depth by 1. Since you are always adding it to the result, size will be increased by 1 and also recurring for the depth. That is why current depth is increased by 1. Hence, let's write it this way. I will always get one node one node only at one level, and that one node is going to be always right node. Because I'm recurring on the right first, I'm recurring on the left. So basically two parts. First part, always first recur on the right, then recur on the left. That way you will be getting the right view, first part. Second part, you're always incrementing the depth by one. The moment you're incrementing the depth by one, that means you're moving to the next level. Then third part, if you're comparing current depth equal to result size, that condition will always be true until you are part of the tree. Why? Because you're always going to add one node that is going to be right, and you're going to increment depth by one. So this condition will always exist true. We have done a dry run for that also in the last class. Okay. And that finally result will give you the answer. You can print the answer. This code is very much extensible. If I have to change it for left view, only condition I need to change is current depth plus one, that will not change. Current depth equal to result side, that will not change. Only thing that will change is I'll recur on the left child first, then I will recur on the right side. That will give me left view of the binary tree as well. Time cooperative big of n, big of h for your recursion space. That's all. Okay, so these are the top view. These are the two views, which is left and right. Now let's talk about bottom view and top view. What is bottom view of binary tree? Bottom view means would explain space complexity. Space complexity is big of h for recursion. Okay. See, what you're doing recurring here is every time you're going for recursion, you're going to go for each of the different levels you're going. So current depth plus one, current depth plus one, I'm recurring on different heights I'm moving. The different heights that you're moving, that will be called the number of time recursion calls are made. So total how many number of calls? Big of h, which h is the number of heights. You're always moving current depth plus one till root is not equal to null. It means you're going to visit all the heights of your binary tree. So till it becomes big of h, that will become a number of recursion call. That's why big of h recursion space. Okay. Coming to this. This is bottom view of a binary tree. Pretty much similar code will be used for top view of binary tree also. What does the question says? A tree is given. What do you mean by bottom view? Bottom view means if your eyes are here at the bottom, how will the tree look like to you? So if I look at this, my tree will look like I will be able to see 5, I'll be able to see 10. Here also shadow will come. Just like in the case of left and right, there was shadow, there is also shadow. The only difference is the shadow which will cover is I will not be able to see 8 because they fall in the same line of sight. Same line of sight, only first object is visible to human eyes. Until unless they differ in height. Okay. 10 and 8, since they are on the same line of sight, you will be visible 10 only. 8 will be hidden. Similarly, 3 and 20 fall in the same side, so 3 will be visible, 20 will be hidden. 14 and 22, only 14 will be visible, and 25, only 25 will be visible. So one thing is for sure, some values are overshadowed by the others. These are the example because they will be visible from bottom line because they are in the same vertical line. Or same vertical line, or you can just simply say same line of sight, whatever way you want to write. Okay. Then for left and right view, my shadow logic was easy. Shadow logic was easy in the sense I can just compare whatever left and right view, I can increase the current depth by 1 and recur for left and right. But this is not the case here. This is not the case. I have to think for something else. I have to think for some other shadow logic. So how does the shadow logic looks like here? My shadow logic is for each of the line of sight or vertical lines, whatever you want to call, each line of sight or vertical lines, I want to make only one tree or I want to make only one node to be visible. And that node should be the bottommost node that should be visible. So shadow logic for bottom views, I'm going to create vertical lines, or you can also say line of sight, to separate based upon horizontal distance. Why separate based upon horizontal distance? You can use any parameters you want. Only thing is each one of them should be different. In case of levels are already different. So I can say current depth plus 1. But in case of vertical lines, I need something to distinguish. That is why I kept the horizontal distance. And it makes sense. All vertical lines, all lines of sight, they will be distinguished by horizontal distance. You can figure out some more property also. I'm not saying this is the only property. The only idea is to keep it distinguished. You cannot overlap first line of sight with second line of sight. In case of levels, it is very easy. You can just say current depth plus 1. But I cannot separate two vertical lines based upon current depth. I cannot do that. Horizontal lines, I can do that. So verticals, if I have to separate, horizontal distance is one of the good criteria. So I can create vertical lines to separate based upon horizontal distance to keep it unique for each vertical line or line of sight. I put the root as 0. Right, if I'm moving to right, I'm going to say it positive. If I'm moving to left, I'm going to say it negative. Okay. Now, if there are multiple nodes on the same line of sight, every time you're using vertical line, let's use line of sight as well. If you're going like this, if there are multiple nodes on same vertical line or line of sight, then you have to replace with the node at the highest step. For example, this 20 and 3 will be counted. 20 to 14, 14 will be counted. So now we move converted, replace with the node at highest step. This is fine. Now we convert this approach to a logic. Logic is vertical line will contain horizontal distance, unique values. Need both height and node for each horizontal distance. Why? Why do I need both height and node? First of all, I need to check which one is at the highest depth. So I will need the height. Second, the moment I find which one is the highest depth, I need to replace that. So I need the node. So I need both height and node. It's going to be a pair. Okay. Now we convert into code part. I need unique values of horizontal distance. That will become my key. I need something like this, horizontal distance and node and height. I need this kind of a structure. Okay. This structure will actually resolve down to, let's copy this. Let's paste this. This is something you need. And which data structure can give it? Data structure is map, which can give it to this. Okay. You need something like this. This can be given a map where the unique values are going to be key, which is the horizontal distance, and value is going to be list of this node and height. Let's make it a pair. Okay, pair. Then we move to the code part. We write the code for it. Let's have a look at the code. Java does not support pair by default. You have to create a pair class by your custom pair class. You have to make, you have to do until unless you're coding in Java, FX, or Guava. These versions support, but core Java does not support anymore. C++ supports a pair. Python supports a pair, so you can directly create a pair. But in Java, if you want to create a pair class, you have to customly write the logic for pair class. That is why I've kept it as an integer array, but it will contain only 2 values. It is a pair only. Okay. Now coming to this prim bottom view DFS, what I'm going to do is integer current depth. This is the height. HD means horizontal distance, integer and map. Now coming here, what I'm comparing is if root is null, returning. If vertical line distance is not available. So if it is not available, this is the very first node that I'm visiting in that line of sight. I'm going to put in the map. If it is already available, so like this line of sight I've already visited, now I need to check which one is the current depth. If current depth is greater than equal to temp1, which is my new depth, then I'm going to replace the temp with this and I'm going to put in the map. Whichever node is present at the highest depth, I need to replace with that. Okay. Then I'm recurring for left, I'm recurring for right. That will give me the answer. That's all. That was bottom view of DFS. Bottom view of binary tree. Is this question available on any platform? I'm not sure if bottom view is available on any platform. It might be available on Geek for Geeks. Check out Geek for Geeks. This might be available there. Okay. Then you move to next question, interview bit. Okay. Somebody has pointed interview bit, it is available. So you can solve for interview bit as well. Okay. Cool. Next is top view of a binary tree, which is asked in Amazon. Obviously, tree is the favorite topic of Amazon. This time, exact opposite case, eyes are on the top. So vertical lines of sight, whatever the first node you're visiting, that is going to be your answer. So you don't need to replace anything. Pretty much same shadow logic, same code. Only thing is that you don't need to replace anything. So this will work for top view of binary tree. This part we're done. Then you move to another important interview question. So after completing left, right, top view, left, right, top, and bottom view, we move to zigzag ordered level traversal. This is important. Read code 103 asked in Google. The question is, have we created diagram? No, we have not created diagram. The question is, you have to do zigzag level order traversal. So left to right, then right to left, left to right, then right to left, so on and so forth. So based upon levels, you have to do. Your output will be list of list, which will be vector of vectors or array list of array list, whatever. Each node is going to be a list. So each node means each level. Each level it should be, not each node. Each level is going to be a list which contains left to right or right to left based upon which level you are. And final answer will be the list of list. Now let's come to the solution part. This is solution using BFS. You go to each level and figure left to right or right to left based upon count of level. You can solve, this will be definitely solved by BFS only, right? So coming to this, list of list integer answer. Now if root equal to this, I'm calling BFS helper. Let's go to BFS helper. What you're doing is you're creating a queue of nodes. You're pushing the value of root. Till your queue is not empty, you're printing the size of the queue. And this is the level node list. This will contain result of nodes at one particular level. It can be left to right, it can be right to left. That we have to see. Okay. We're traveling for till that size, whatever the size in that result node. Now what you're going to do is you're going to pull or you're going to pop that value from, this is not called pop, this is called poll, just to be clear. Pop is a reference which you use in terms of stack rather in terms of queue. So going to pop that value, which is temp. Then you're going to add it to your level order list. You recur on left, you recur on right. So until now, until this part, this code is BFS only. This code is completely BFS. If somebody asks you to write the code of BFS, this is exactly the code of BFS. Okay, that's all. But Now, after this, we have to modify a BFS a little. How we have to modify? After you got the output for one particular level or multiple levels, now you need to check for that level. Should I reverse it or should I not reverse it? What is the logic that comes whether I reverse it or not? That comes based upon after this for loop, I have left to right values of a particular level order. Based upon odd or even, I'm going to change the direction. That direction comes, if it's odd level, reverse the level order value. So count modulus 2 not equal to 0. I have reversed it. So 920 will become 29. I'll get the output like this. Okay. And obviously count is going to increase accordingly. Count plus plus will always happen. Cool. So this is 1, 2, and 3. And I'm maintaining upon based upon which value of count I'm going to reverse or not reverse. This is the Java code. It's not like a difficult code or something, but it will take time to write the code. That's what I'm saying. Okay. O time, O space. This is going to be your code. This is iterative code. Easier code or shorter code is this Python code, where all you are doing is it is very self-explanatory as well. You're keeping a result as the final answer. Direction is giving us 1. Reverse will take another take big of n. Reverse will take big of n. Agree. This will be big of k to be precise. It's not going to be big of n. So big of k it's going to take. But I don't think that is going to complicate much more of the complexity because this collection dot reverse, it will not contribute to much of the complexity. Ultimately, you're traveling the nodes of the list, plus you're doing some number of reversals. So that will not contribute like big of n into k kind of complexity. It will not contribute to that much. Okay, cool. So we can claim it as big of n. All nodes have been visited only once. Now coming to this, and even this collection dot reverse, right? You can even further subtract it. Like you can use 2 pointers, do it in big of n by 2. Many ways are there to optimize, but it's not like it will go big of n square, that kind of logic. That will not go. Okay. Now coming to this class solution, what we are doing here is, this is the result, where is the 2D list, and this is the direction I've kept as 1. While I'm in the queue, this is my level order. Level order means for that particular level, this is going to the list of values. I'm going for left, I'm putting, if the left is not empty, I'm adding left, I'm recurring on the right, left and right. I'm appending based upon direction. Now direction I'm multiplying by -1. So odd one, the trick logic is this. If one you multiply, -1 you multiply even number of times, it will become 1. -1 you multiply odd number of times, it will become -1. And in Python, array list or array or any list of -1, hyphen -1, that gives you the reverse order. So this is what I'm exactly doing here. So the moment it becomes odd, it's going to go in with the reverse order, else it's going to go in with the right order. This is what it will solve for me. Okay. This part is fine. Time complexity big of n, space complexity big of n. Then we move to LCA. This is really good question. LCA questions are usually asked. Lead code 236, we were in lowest common ancestor of a binary tree. Let's see. You're given a binary tree, you have to find the LCA of 2 given nodes. We're going to discuss all the approaches. What is the right approach to find an LCA? First for binary tree, then we'll go for BST. Okay. Example is here. The input output is given here. Now let's come to the understanding. Understanding of LCA is LCA of 2 nodes N1 and N2 is defined. LCA is first of all lowest common ancestor. As the name says, lowest common ancestor. And LCA of 2 nodes is defined as lowest node in tree that has both N1 and N2 as descendant. Descendant means anything below, ascendant means anything above. So N1 and N2, they can be descendant of each other also. It means they can belong to the same subtree. Now let's have a look. LCA of N1 and N2 is defined as the common ancestor of N1 and N2, which is farthest from the root. If there are large number of nodes in the tree, but top view nodes are less, still we have to traverse the whole tree, right? In the top view, if there are large number of nodes in the tree, but top view nodes are less, still we have to traverse the whole right node. I didn't get this question. Give an example. You're saying, okay, first understand, whenever it's going to be very nested tree in the sense, very large tree is there, you just want to visit the top. Top node will always be less, that is for sure. Because at every height, it's gaining 2 raised to the power h. And I just need the first one. You're still not traversing. You're still not traversing. Let me show you the code of top view again. This part, I'm not traversing it here. Okay, the traversal part comes into here. So you're not traversing it again here. The very first part you got, you go put in the map. That's all. Okay. Anyhow, coming back to this, so we're talking about another definition of LCA. Another definition of LCA is common ancestor of N1 and N2, which is farthest from the root. Farthest from the root, or which you can say lowest in the tree, whatever way it works for the same way. Let's take an example. This is 1, 2, 3, 4, 5, 6, 7. If I take LCA of 4 and 5, Their common ancestor, which is largest from the root, or whichever is lowest in the tree, that is 2. Output is 2. 1 and 2, both are common ancestor, but LC is 2. Root will always be a common ancestor for any two different nodes to take. Okay. Then we talked about LC of 4 and 6. 4 and 6, it exists in left subtree, it exists in right subtree. There is nothing common apart from the root. So output will be root. LC of 3, 4, again, they happen in to be different subtrees. So output will be 1, which is the root. 2 and 4, they are part of the same subtree. So 2 comes before, so it will be 2. This is, we have got till the definition of LC. We have not written the code for it. We have not thought about the approach of it. We just talked about what is LC. Question I've already shared. This one was LC. Everybody clear with it? What is LCA? Everybody clear with it? Give me clear in the chat. LCA of a binary tree. Everybody clear? I'm going to take this. I'm going to start this one template. Also, moving starting the template. We'll go to graphs. We'll discuss that. But just to tell you, in the graph, these are the list of topics we have. This constitutes 70%, includes theory application, representation, adjacency matrix, adjacency list, BFS, detect cycle in a graph, BFS in disconnected graph, all of this. Advanced part, which is 30%, which is DFS, MST, and shortest distance. Although a lot of interview questions are asked on this as well as on this BFS part. Okay, we are going to see. Pretty much BFS and DFS is something which is there in the graphs. Any algorithm you take, any particular algorithm you take in the world, not in the world, any algorithm you take on that which is implemented in terms of graphs, it is just an enhanced version of BFS or DFS. You take topological sort, you take Dijkstra, you take Frame, you take Kruskal, Benman, Floyd, or anything. All of them are built on the top of BFS, DFS. So understanding BFS, DFS is most important. But prior to that, let's solve these 3 questions that we have listed, and then we are going to continue from there. What is this? Anyhow, coming to this part. Have you guys tried this question as part of homework? Have you guys tried this question? Yes or no? No. Okay. Do try out the question, guys. Otherwise, it will. I will do today. I will discuss right now. So you can do one thing. I'll discuss the approach, write down the code, and submit. Questions link I've already pasted here, right? I'll discuss all the approach. You guys can write the code. Nothing too difficult. Write the code. Okay. Now let's come to this part. LCA concept is very clear. So what is the LCA? With this part is clear. Now let's talk about how can I find the LCA. Question is clear. 2 nodes are given, N1 and N2. You need to find what is going to be the lowest common ancestor for N1 and N2. This part, all everybody clear? Okay. Now let's talk about solutions to find LCA. There are 2 ways, guys. One is brute force, one is optimized. What is the brute force way to find LCA? Brute force to find LCA. The brute force way is, if I want to find LCA, what do I need is lowest common ancestor. It means it is going to be the lowest node in tree, which will contain both N1 and N2, right? So if I do a path from my root to N1, if I do a path from root to N1, if I do a path from root to N2, and all I need is last common element in the path, that will become my LCA. Yes or no? Visualize it before even thinking about code or anything. Visualize it. It is the most important part. Let's see it here. Let's take this LCA of 4, 5. We're going to make it 2. Let's take this example. That is sufficient here. This is what I'm referring to. So if I say path from root to 1, so root to 4 is going to be what? Root to 4 path is 1, 2, and 4. And root to 5 path is 1, 2, and 5. What is the last common element we have? What is, are you going in the reverse direction in the tree? No. No, I'm not going in the reverse. I'm just going in the root to the child. Understand this. We are just creating root to child. We are not modifying the structure of the tree. I'm not going to make up child to parent kind of a pointer. I'm not making that. So it's just root to the child I'm traveling. Last common element that we have is 2, which is my LCM. Agree? Agree. And that's technically correct, right? What you're saying is, what is lowest common ancestor? Lowest common ancestor is the lowest ancestor which is common in both N1 and N2. What does that mean? If I create the path, visualize, that's what I'm saying again. Code part is not difficult, visualization is more, not difficult, visualization is more important. If I'm talking about this, and if I'm talking about this, and I'm claiming the lowest common ancestor, which is going to be ancestor of both of them, it has to come. If I take this, if I take this, whatever is the last value which is common there, because obviously they will differ in that part, but whatever is the last value which was common, last common, that is going to be my LCM, right? So in this case, 2 is come out to be your LCM. You can take any test case, you can verify with anything, that will become LCM. Okay. You want to verify with something else? Let's verify with something else also. LC of, let's talk about 4 and 7. Extreme nodes. What will be the LC here? What will be the LC here? Come on, guys. Correct. One belongs to left subtree, one belongs to right subtree. There is going to be root only. So if I say root to 4, 1, 2, and 4, if I say root to 7, it's going to be 1, 3, and 7. The last common element, which is going to be your LCA, it's going to be 1. So one approach is clear. I can take a path from root to N1. I can take a path from root to N2. Then I can check whichever is the last common path. I can get the answer. This part clear to all? This part clear to all? This is the brute force way of doing this. Everybody clear with this approach? We'll go to optimize later. How will we know that what path to take and it is not BST? How will we know what path to take and it is not BST? I didn't get the question. So simple, you will be doing left to right traversal, right? Simple, you will be doing left to right. Just like you do normal DFS. In normal DFS, you recur for left first, you recur for right first. That's how you do it. That's how I'll do it. See, understand this. It's going to be from a root to a particular node. So root to particular node, how you do it? You're not checking if that is present or not. You'll keep on recurring. You'll be keep on doing DFS, left to right. First you recur for the left, then you recur for the right until you find that value. That's all. In BST, you have the advantage. You have to choose left or right. But in case you are in a binary tree, I think we have done this question. Search in a BST. Same question is a similar question is there. Search in a binary tree. When search in a binary tree, you don't know which value to search. So in that case, what you're going to do? You're going to recur for left. If it exists in left, good. Else you're going to recur in right. Both ways will happen. That is why in terms of BST, complexity was big of log n. In case of binary tree, it will be big of n. Because in worst case, we'll be traveling all the nodes. Okay. This is just like unsorted array. If you have to travel an unsorted array, big of n complexity for search. Unsorted array, big of log n complexity. Everybody clear? Okay. So this is a brute force approach. So if it talk in terms of complexity, complexity would be what? Complexity would be first root to n1, second root to n2, third the two arrays that you have created. Because if you're maintaining which one is the common part, you have created two arrays. So let's call it store in array 1 and store in array 2. Something like that. Array 1, array 2. The two arrays that you are having, that also you need to compare, right? Check for last common value in array 1 and array 2. This, all of this operation will be taken into the picture. All agree? Anything that we missed? Root to n1 you have traversed, root to n2 you have traversed, that for our last common values, yeah, that will be the complexity. Time and space you guys can write big of n plus big of n plus big of whatever that size. That will also go in the worst case big of n, big of n, big of 2 into n. 2x iteration you are doing in the case of these trees. This part clear to all? This approach clear to all? Okay. Now, what is the drawback with it? Now, drawback or negative side here is This is asking me to do two iterations of the tree. Two iterations of tree it is asking me to do. So can I solve it in a single traversal? That can be a good follow-up question. And second thing is that extra space is wasted for two arrays. I mean, you can use a variable also. Based upon that variable, you can compare. If it is not equal, then you can do two variables you can compare. But anyhow, if you're storing the path, then extra space for two arrays taken. So both in terms of time, both in terms of space, I am facing some overheads. Now, follow-up question comes: Can it be solved? Can it be solved in single traversal? Is it possible to find in a single traversal the LCA of two different nodes? The answer is yes. Okay. Now we go for optimized solution. Optimized solution is using single traversal. How do I know the logic for single traversal? There would be cases around it. Okay, there would be cases around it. Case number one is if n1 or n2 matches the root. If any of these values matches the root, then obviously answer, or let's say LCA, is going to be the root. If you're checking LCA of any node with the root, what is the LCA? Root. Okay. Case 2 is n1 is not equal to root, n2 is not equal to root. So both n1 and n2, or let's write it this way. If n1 and n2 lies in left and right subtree, then what will happen? If they are present in left and right subtrees, in that case, their LCA will be what? Their LCA will be root again. This example I'm talking about here. Let's take out this example that will be helpful to understand. Copy this, paste it. Let's make the cases. Case number one, if you're talking about 1 and 4 or 1 and 5 or 1 with anything, output will be always 1. Okay. Let me add one more case. This part. If you take 1 with 6, for example, it will be 1. LCA of any node with root is root. First part. Okay, this is case number 1. Case number 2, if n1 and n2 lies in different subtrees, left and right subtree, LCA will be the root. For example, if you're talking about 4 and 7, LCA will be 1. If you're talking about 4 and 5, the root here 2 will be the LCA. Okay. This part. And if they are equal, then good. If not, then recur for left and right subtrees. While you're recurring, now these conditions will exist. Case number 2 here. Another case that will exist is case number 3. If they are part of the same subtree, output is going to be what? Output is going to be what? So if n1 and n2 belong to left subtree, then LCA will be what? LCA will be in left subtree. Okay. If both nodes are not part of different subtrees, then it means in the same subtree you will find the LCA. And last, same like this, case number 4. If both are present in right subtree, LCA would be in the right subtree. That's all. Okay. Now let's look at the cases. First, if any of them matches the root, example 1, 6. Second case, if they lies in completely two subtrees, for example 4 and 6 and 4 and 7, 5 and 6, 5 and 7, output is going to be the root. If they belong to the same subtree, for example 2 and 4, they belong to the same subtree, answer will be in that subtree, whether it is left, whether it is right. So 2, 4, output will be in the left subtree only. And similarly, if I take 3, 7, it will be in the same subtree only. So do we need to add example here? Let's take example here. Example 1, 6. Copy. Add examples for everyone. It will be easier to understand or remember whatever. And we have to let in left and right subtree. Let's take 4 and 7. They're part of same, so let's take 2 and 4. They're part of same. Let's put 3 and 7. Now I think it should be crystal clear to all of you. Have a look at what I have commented here, or not just commented, have a look at whatever I've written in the notes. Let me know if everybody clear. Any doubt, feel free to ask. Easy? Let's write the code for it. I'm going to write a code. What do I need? I need to return a node. I don't need to return the value there. I need to return the row. Find LCA. LCA of what? Binary tree, not BST. It's a binary tree. What I'm given is I'm given a root. What I'm given is I'm given integer n1. I'm given integer n2. That's it. Only these three things would be given to you. First thing first, if your root is null, check for the base case. What do you return from there? You return null from there. This is the base case for an empty tree. There is no LCA. Okay. Now, if n1 and l2 is there, so if root dot data or root dot value, whatever it is, equal to n1, or root dot data is equal to n2, in that case, return root. This is the case which I am referring to, case number 1. Okay, this part. Next part, if it is not, then you will start recurring for left and right. So node left underscore LCA, you're recurring on the left. So let's write it here also. Left LCA, find LCA binary tree. All you have to do is you need to pass your root dot left this time, n1 and n2. This is your recurring on left. Copy, paste it here, name it as right LCA. That will become root dot right, n1, n2. Now what? Now you have recur on left and right. What you have to do is, if both values are lying in the same subtree, that would give you the answer. Otherwise, other one would give you the answer. Okay. Same subtree means if both of the above calls will return. Let's take case number 2. Case number 2. If n1 and n2 both lies in the left and right subtrees. So if both are present in left and right subtree, it means this left LCA will not be null and this right LCA will not be null. Agree? If n1 and n2, let me write it here. If n1, example I'm giving, n1 lies, or instead of that, let's write, if n1 and n2 lies in left and right subtrees respectively, then it can be either way. N1 can be left, N1 can be right, whatever. I'm not judging on that. But I'm saying is all of them, both of them exist in different parts. Then left LCA and right LCA, both would be non-null values. If they are part of the same subtree, then only one of them will be null value. All agree? If left and right LCA both are not null, it denotes that L1 and L2, they are both present. They're both present in different subtrees. If any one of them value becomes null, it means now they're present in one of the subtrees. So let's put that condition. If left LCA is not equal to null and right LCA is not equal to null, it means they're present in different parts. In that case, my root will become the answer. Okay. Last two condition, case 3 and case 4, let's do that also. Okay. If they're present in left, go for left. If they're present in right, go for right. Okay. Case 3 and case 4. So I have to put if my left LCA is equal to is not equal to null, then my answer will be what? Left LCA. Otherwise, my answer will be right LCA. Return left LCA else, return right else. This part. Okay. And this would become case 3 here. This would become case 4 here. Cool guys. Have a look at the code. I'm just getting it back here. Simple, straightforward code. I've added a lot of comments, but anyway, that's for your help only. So 1, 2, 3, 4, 5, 6 lines only, but all the comments, the code is looking bigger. It's just 5, 6 lines of code. Have a look at the code. Let me know any doubts. If it is clear, type clear, then we can go to next question. Could explain 1130. 1130, what is happening is, if let's take a case where we have put left and n1 and n2 present here. So 4 and 7. If 4 and 7 are present as part of different, so you move to 4, you move to 7, right? This condition you are going to hit, this condition you're going to hit. So left LC will never become null and right LC will never become null. Visualize it like this. Visualize it like this. Where is it? This is the n1, this is the n2. Okay. You're recurring for n1, which is on the left part, you're recurring for n2 on the right part. If they are present in both left and right, in different left and right, in that case, what's going to happen? This value will never become null. Null becomes what? You're trying to find it, you didn't find it. You're trying to recurring on left, you're trying to recurring on right, you didn't find it. Let's take another example. Let's say you're talking about 4 and 2. You're recurring on left, you will find this. So whatever base condition I've given in recursion, that will happen. But will you find anything on right? Will you find anything on right? No. You will find nothing on right. That value will become null. That value will become null. But here, if it is present left and right, neither your left will become null, no right will become null. So if both are present in the left, then left LC will not become null. That is when you're returning left LC. If both are present in right, your right LC will not become null. You will return right LC. If both are present in different nodes, both are present in different subtrees, then you will return left LC, right LC, both are present, then I'm returning the root value. That is what I've written here. Okay. Cool, guys. Have a look at the code. Give it clear in the chat if this is clear, so we can move on to the next question. Please submit once on lead code. I have not checked the syntax on lead code. Let's check the syntax on lead code as well. Which question number is it? 1. Okay, 236. This is there. Let me just open this. Public tree node, lowest common ancestor, P and Q. Let's move to this part. The code we have written, let's modify it accordingly. Copy and paste here. Coming to this, we need to modify the logic here. I don't need of this. Okay, tree node is given, so I need to compare with data, p.data and q.data. Okay, that's fine either way. So let's come here. Root is fine. Root.data equal to p.data. This has to be q.data. What else? P1, this will become P and Q. P and Q. This will become tree node. So copy and paste, copy and paste. What else? If it is not null, it is not null, you're returning root. Yeah, it is value. Yeah, this is value. Value, 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 value. What next? You're returning on left and right, P and Q. This is fine. This function is lowest common ancestor. Okay. If it is not null, that is fine. Left LC not null, you're turning left LC, right LC. Let's try run. Let's see if we missed any condition. This looks fine to me. Time with space complexity. Let's write that also. Time complexity big of n. Recursion space complexity big of h. Whatever height of the tree. Let's submit. Passed all test cases. I solved it last time. Not last year, 6 months ago. Yeah. Anyhow. Cool, guys. Then let's take this. Let's take this. Or it's already there, so nothing to take from it. Anyhow, let's come to the next question, which I was talking about since we are already on lead code. Next question I was talking about this. Okay, I have written the code, so let me just comment that first. This question clear to all, guys? We have submitted the solution and everything. This is clear to all. Okay, I'm not closing this tab because I'll be using this tab for analogy, right? Coming to the question, lowest common ancestor of BST. So lowest common ancestor of binary I've done, BST you guys can do. I mean, we'll do it right now only, but nothing much changes are required. Let's see the question. Okay, tell me one thing. Is it easier to find LC in a binary tree or is it easier to find LC in a... LC definition is same, so I don't need to repeat the definition of LC. What do you think? Is it easier to find in binary tree or is it easier to find in binary search tree? Obviously, it is easier to find in BST. That's the purpose of giving an order. Same definition of LC, nothing to repeat it here. There is no point of repeating it here. Let's see the test cases. This is the binary search tree. So if you see P equal to 2, Q equal to 8, 2 and 8, LC will be 6. P equal to 2, Q equal to 4, so 2 and 4, LC will be 2. Definition is pretty much the same. All values are unique because it's a BST. P is not equal to Q. We know that. 2 into 10 to the power 5, so minimum 2 value will exist and range value will exist in 1 billion. P and Q will exist in the BST. Okay. Yeah, one more thing, guys. This is important part. P and Q will exist in BST. All of this complete approach is based upon the fact that both are present. We're not talking about a case where it is not present. We're only talking about the case where it is present. So we're checking in left, we're checking in right, and recurring for left and right. Here also in condition, it must be given, yeah, as I said. So let's solve for this question. You guys gave me the solution for this question before the solution, or you can talk about the approach also because nothing to repeat here. So let's take second question, LC of BST. Come here, 235, lead code. Okay. Question link is here. What else? Question, anyhow, pretty much the same thing, so nothing to change here. Just one thing to change. This is a BST this time. It's not a binary tree, it's a BST. Think about what needs to be changed in the code we have written for binary tree. You want the code for binary tree? Let me give you the submission link also, if I can. Copy link address, this part. So lead code submission link is this, which I'm gonna give in chat as well. This is for LC of binary tree. You want to modify the previous code? I am more than happy, whatever way you want to do. Just make sure you are implementing the right logic for the BST. Again, I'm repeating, this is LC of BST, not of binary tree. And this is the function you need to complete. As on lead code. Okay. Question link, I'm putting the question link also. Cool, guys. Question clear to all. I don't need to mention anything. Only difference is this time is a binary search tree. It's not a binary tree. This time it's a binary search tree, not a binary tree. Question clear to all? Okay. Cool, guys. Modify it. Give it back to me. 30 seconds on clock. I already got 2 answers, which is good. 30 seconds on clock. Quickly give it back to me. Your time starts now. Feel free to modify the previous code the way the logic needs to be modified. Pretty much the same thing. Okay. Think about the intuition also. What is the definition of LCA in terms of a BST? Then we'll come for solution. Okay. Let's discuss that first. Let's quickly make a BST. Let's put anything. 20, something less 8, 22. Less than 8, make it 4. 4, 8, 12. 4, 8, 12, 20, 22. Make few more. 4, 8, 10, 12, 14, 22, 26. This is fine. Let's come to this, come to this, come to this. Okay. Is it a BST? Is it a BST? Of course, it's a BST. Do I know the traversal? You will get the sorted output. It's a BST. Now try to understand what is the right definition of LCA here. If I talk about LCA of 10 and 14, what is LCA? Quickly tell me in the chat. I'm adding few cases. Give answer all in ones. 10 and 14, then do let's 8 and 14. And I want something from difference. So 4 and 22. Anything else I need? 4 and 22 is fine. 8 and 14 have done. That's it. 10 and 22, that is also fine. Cool, guys. I think these three cases will sufficiently suffice. Let me know what is the output here. 10 and 14, whatever is the lowest common ancestor, that is going to be 12. 8 and 14, part of the same subtree, that is going to be 12 or what? It's going to be 8. Right? 4 and 22 belongs to different subtree. It's going to be 20. Same logic, nothing will change in the definition of BST. But the only definition in the BST, only thing that will differ in terms of BST is this. Understand one thing. N1 and N2, right? So if you're talking about two different nodes, N1 and N2, one thing is clear that N1 and N2, one value will be smaller, one value will be larger, whatever it is. Now, if you're comparing between two trees, or if you're trying to compare between two subtrees, N1 and N2, LCA in a BST would be what? Would be the first, LCA in a BST would be the first node which lies in N1 less than equal to LCA less than equal to N2, assuming that N1 is less than N2. Assuming N1 is less than N2. This will be the first LCA, or this will be the first node which will satisfy this criteria. Okay, take an example. 10, 12, 14. Less than equal to, less than equal to. What was the LCA? LCA was 12. Yes or no? LCA was 12. Yes or no? Yes or no? We just say the LCA was 12 here. Now, other cases, for example, if they're part of same subtrees, if they're part of different subtrees, even in the case of, you see, 4, 20, and 22, 20 will be the LCA. Only in the case of 8 and 14, answer will be different. Why it will be different? Because they are part of the same subtree, whether left or whether right. Now, using the properties of BST, I know one thing. Something is called my current node and something is called my N1 and N2. I just want to check if my current node is the LCA or not. So let's talk about this. Traverse in BST. All I have to do is I need to check if my current node is greater than N1 and N2. It's greater than both N1 and N2. Current node is greater than N1. Also, it is greater than N2. What does that mean? The value that you're trying to search, you are at a position which is greater than both N1 and N2. Take an example. You want to check for 8 and 14. Your current node is 22. Will you find in the right subtree? Example I'm writing here. This is case number 1. Example is your current node is 22. Your N1 is 8. Your N2 is 14. If you have reached to a place, if you have reached to a node which is greater than both your current node and left node. So 3 cases are there. This is case number 1. If it is between, so whatever the first value is satisfied, that will get the answer. Whatever the first value that satisfies, that will get the answer. Case number 2, let's write it this way. Case number 1. Traverse in BST, let's make it on the top. If your current node is greater than N1 and your current node is less than N2. In that case, answer will be current node. This example I've given. Case number 2, if current node is greater than both N1 and N2. If current node is greater than both N1 and N2, then what is going to happen? Then what is going to happen is You're going to compare it's greater than both n1 and n2. If you are at 22, you want to check for 8 and 14. I need to go left or I need to go right? I need to go left or I need to go right? I need to go left. So go left. Let's look at case number 3. Case number 3 is this. If your current node is smaller than all of them, case number 3, it is less than n1 and it is less than n2. So take an example. You want to check for 8 and 14 and you are currently at 4. So currently at 4, we have to move to right. That's all. And case 4, you just return the root, whatever root is there. That's it. These are the 4 cases. First case, if a value is lying between n1 and n2, if the current node lies between n1 and n2, it means that is a junction where it is connecting. That is going to be your LCM. Second, if you're at a position which is greater than both n1 and n2, it means you have to go for the left because n1 and n2 can only be found in the left. If it is less than n1 and n2 both, it means it can only find in the right, so recur to the right. Else, final case, you return the root value. This part clear to all? This part clear to all? Okay, let's directly write the code on lead code. Then we can submit from there itself. This is lowest common ancestor of a BST. Let's write the code. P and Q, same thing are given. So if this is root dot value is greater than P dot value and then root dot value is greater than Q dot value, I am going to recur for root equal to root dot left. This is first part. Okay, I'm going to recur for root dot left. If I find out that else if root dot value is less than n1 and it is also less than n2, then what? Recur for right. Root equal to root dot right. This part recur for left and copy and paste. This part you're recurring for right. Delete from here as well. Okay, now what next? Else I'm going to put a break and I'm going to return my root. Put iterative logic while your root is not equal to null. This part while will end here, this part, and you're going to return root, this part. Okay, that's it. So if n1 and n2 they are part of the smaller, you're going to recur on the right. Else you're going to recur greater, you're going to recur on the left. This is fine. Else it equal to break. So what is the common value get? You'll get the answer. Okay. Prior to that, let's take approach that we have written here as well. Cool. Now it looks better. Let's try to run the code. It's p dot value. Okay. Time complexity big of n space complexity big of h. Space complexity big of in case of iterative solution. If you have a recursive solution, then it will become big of h. But this is iterations, no space being utilized. 9 milliseconds, which is really fast. So we are able to submit this as well quickly. Cool guys, let's take this code. Let's move next. Time and space complexity also. Let's move it to Sublime. Cool. Come back to Sublime. Give me clear if everybody clear with this. Give me clear if everybody clear with this. So we can go to next question. Okay. Let's move to next question. Somebody asked this question, but I'm not sure who asked it, but it's a good question. Let's discuss that also. I forgot what was the question. I have listed here. Yeah. This question, what was it? Lowest common ancestor in case of deepest leaves. Somebody asked this question. Let's discuss that also. So moving to last question. Then we are going to start with graphs. So one more variation on LCA. Two we have done. This is the third question. This is the last variation LCA. Let's see that also. Lowest common ancestor of deepest leaf, 1344 likes and 100K submission. Not that popular question, but question is good. This question is same as 865, smallest subtree with all deepest nodes. Let's see that also. Smallest subtree with all deepest nodes. That is higher ranking, 2063 and almost 157K. Anyhow, by solving one question, we are able to solve both the question. So given the root of a binary tree, the depth of each node is the shortest distance to the root. It is the smallest subtree that contains all the deepest node in the original tree. Okay, same question. So it's a good thing. Somebody has recommended this. Now we're able to solve two questions at once. Let's have a look at the question. The question says, if given the root of a binary tree, you have to return the lowest common ancestor of its deepest leaf. Now this is important. Lowest common ancestor of its deepest leaves. What do you mean by deepest leaves? That is given here. Node of a binary tree is a leaf, and if it has only no children, we know that. Depth of root of the tree is 0, depth of the node is D, then depth of children will be D plus 1. That is subjective. Some people write it as root as 1, some people write it as 0. So this case is mentioned as 0. Okay. Main thing is this. If depth of a node is D, then depth of each of its children will be D plus 1. Agreed. Lowest common ancestor of a set S of nodes, the node A with largest depth, such that every node in S is the subtree with rooting. Got it. Let's take an example. 3, 5, 6, 2, 7, 4, 0, 1, 8. The deepest tree or the lowest subtree, as you can call it, deepest leaves, 7 and 4 are the deepest leaf. We need to find the LCA for the deepest leaf. So the deepest leaf will be 2. So in the previous question, P1, N1 and N2 were given to you. Two different nodes were given to you. You have to find it. This time, nodes are not given to you. So two things you have to do. First, you need to find the deepest leaf nodes. And then for those deepest leaf nodes, you have to implement the logic of LCA. LCA logic will remain same. Same LCA for binary tree remains same. The thing is, in the previous question, or this question I'm talking about, of a binary tree, you are actually given which node you want to check for the LCA. So N1 and N2 were given. This time, no N1 and N2 is given. You have to find N1 and N2 such that N1 and N2 are the deepest leaves. And from those deepest leaves, you have to find this answer. That is why it becomes a tricky. Not a tricky, it's just one extra things that you have to do. Same question as 865, values are unique, 1 to 1000. Node value can be 0, but node is not empty. So tree is not empty. Okay. Let's take this question. Let's try solving it on Sublime. Lowest common ancestor of deepest leaves. Take this, move it. Okay, pretty much everything we have written here. This example 3. This is fine. Let's move now. Cool, guys. Before starting your timer, look at the question again. Let me know any doubt in the question. This is your question. Let me know any doubt in the question. Question is clear. Give me clear in the chat. The only difference between the first question, second one was a BST, so I'm not counting that. The only difference between the binary tree question and this question is that you were given two different nodes and you have to find the LCA. Now you are not given any nodes. All you are given is a root. So if you check the parameters, you're just given a root. You need to find out what will be the deepest leaves. Then you need to find out what will be the LCA for that. That is the only variation. Question clear to all? Give me clear in the chat if question is clear to all. Come on guys, be quick. Question clear, cool. This is the code that you need to complete. Feel free to write in whatever language you want to write. Okay, 30 seconds on clock. Anybody who's yet to answer, I'm just giving last 5 seconds, else we'll discuss solution. Last 5 seconds if anybody else had to discuss code or approach or anything. Okay, enough time, let's discuss the solution. Understand how this is different from the previous question. What you need to do is, I need to find the deepest leaf nodes. First of all, first part, I need to find the deepest leaf nodes. Then I need to apply the logic for LC for those deepest leaf nodes. For deepest leaf nodes. This is what I need to do. Now, when you say deepest leaf nodes, how do you find the deepest leaf nodes? What is the definition of a deepest leaf nodes? For deepest leaf nodes, it means you have to go to the highest depth. Yes or no? Whichever node has the highest depth, that will be deepest leaf nodes and no children. That is the definition of leaf nodes. Okay, there are two things. Leaf node means no children, deepest leaf node means highest depth. So you combine both of them, so you will get the highest depth with no children. This part clear to all? This part clear to all? Yes or no? Okay. Now coming to this, I need to, if I turn this intuition into approach kind of a thing. So this is my intuition. If I turn this intuition into approach, my approach would look something like this. Recur for heights. Recur for heights. Or use the same function for heights. Find maximum height and leaf node. Now I need to maintain that order. Some maximum height and corresponding that leaf node, that order needs to be maintained. Or that key value pair, or it can be a pair. Pair or a map, where you can do what? You can tell that for this particular node, this is a depth, which will store something like this. For node, this has to be a depth. That ordering needs to be stored somewhere. You can use a pair, you can use a map, whatever you want to do. Okay. And then what you have to do? Return the LC. After that, you can return the LC for the same. Let's connect charger here. Okay. Then you have to return the LC for the same. That is something which you need to resolve. Now, let's directly go to the code part. This approach is pretty much self-explanatory. Java, C++, Python, whatever. Have I solved in C++? I've already solved in C++. Okay. Let's solve this time for Java in that case. Or anything is fine. Even if it is, let it. Okay. All I need to do is either you're keeping a pair or you're keeping a map. It's totally your choice. If you want to keep it a pair, that's fine. You want to keep it a map, that is also fine. What do I need is LCA deepest leaf tree node. First thing, let me increase the scene a bit. Coming to this. Okay. Very first thing which I need to check. Let's get the chat window here. If it is not root or if the root is empty, in that case, I'm going to return null. I'm returning tree node, so that's why it has to be null. It was integer, I could have saved left. I would need some function to calculate the left, calculate the height. So integer left depth equal to, let's make a function integer count depth or height, whatever it is. Same code for height will be the code for depth that we have already done. It will contain tree node star root. So copy this. That's it. Only one argument is required. Tree node star root. come here. Okay. Now what? If the root is not present, if not root, then you are returning 0 from there. Okay. Else, if not depth, we need a mapping here. So to create a mapping, let's write the approach also. It will be easy to write. This. Yeah. Let's write the approach here. Okay. I need to store that mapping somewhere. So let's create a mapping, an ordered map, where I need a node, 3 node star, and I need what? I need an integer. That integer is denoting its depth. So this is storing node to depth or node to height mapping. Now what? If not root 0, then you have to check if it is present or not present. If not, depth dot count root. If it is not present, in that case, depth of root is equal to 1 plus. How do you calculate the height? You calculate the height plus 1 plus left height and right height. So 1 plus maximum of recur for this function, count depth of left, comma, count depth of right. Okay, I'm writing it here. Height formula is 1 plus maximum of left height and right height, just to be clear. Then if you found the height, so this is the if condition. In the else condition, if you find the height, you are just going to return depth of root. Let's keep it here. That would make more sense to understand. Now what next? This part, this part, this part. Let's delete this from here. Keep this here. Now the code looks better. This is if part, this is else part. If height not calculated, then you are calculating the height. Else, if already calculated, you return by default. Okay, return depth of root, this part. Now coming to this left height and right height. Left depth will be count depth. You're passing the left child, root left, and copy. You need to find left depth, you need to find right depth. What else do you need? You got the left depth, you know the right depth. Now, when you're talking about deepest leaves, it is possible that that deepest leaf, left depth is more or right depth is more. So if both are equal, if left depth is equal to right depth, what does that mean? What does that mean? If left depth equal to right depth, this means both leaf nodes are at same level. That's all. Both leaf nodes are present same level. So returning the root in that case. Next condition can be if left depth is less than right depth. In that case, I need to go for the maximum one. I need to go for the maximum one. So I'm going to return, just recur this function for maximum one. Root left. Okay. Sorry, not root left, should be root right. Maximum one. Okay. Copy this. And last part, this would be else. Here you will be recurring for left part. That's it. Straightforward code, easy to understand. What we are doing here is, before submitting it, let's try to understand what we are doing here. What we're doing is, I'm calculating two things I need. I'm not given any nodes. I know how to find LCA, that we can find, but I'm not given which nodes to find the LCA. All I'm told is you need to find the deepest level nodes, deepest level leaf nodes, then you have to find the LCA. Okay. So what I'm doing here is, in order to understand which is the deepest level, with every node I'm visiting, I must know which level I am. Agree? In case I want to know deepest, I need to know every level, every node that I'm visiting, which level I am. That is what I'm maintaining this mapping here. So with every level, I'm giving whatever the level I'm currently at. Okay. Which I'm storing in left depth and right depth. If both are from the same level, my root will become the LCA. If it is right depth, I'll recur to the right. If left is more, I'll recur to the left. Okay. And same logic I will follow. Now in this height, what I'm mapping, I'm just calculating height logic, 1 plus maximum of left height and right height. That's all. So let's solve this. If not depth dot count, non-static member must be called. Reference to not static member must be called. This is C++. Why? Okay. Let's make this private. 69 line spanning array. Okay, something is wrong. Let's see. This is a function depth. Oh, okay. No, there is something else. Line 68 is the error. What I'm trying to tell, if not depth dot count root, reference to non-static member function must be called. Ah, okay. Sorry, my bad. Count is a function. I'm passing it as an error. Yeah. Non-static member function must be called 1 plus maximum of count depth. Okay, count depth of root left and count depth of root right. Okay, wrong answer. Expected was 274. My output is the tree itself. Okay, let's see where we did the mistake. Come back here. I calculated this condition is fine. Left depth I'm occurring. Count depth root and left. This is fine. This is okay. That's it. Right depth and left depth both were same. Yeah, now it is working fine. Anyhow, coming to this time and space complexity, let's talk that also. Big of n, one time visiting every node, space complexity, big of whatever Euclidean space is there. This will be capital C. Cool guys, let's submit this. Let's see how many submissions it will defeat. Okay, come in here. 141 ms is very high. 16 and 20 ms I have solved. Let me submit again. One moment. Why it is so high? Anyhow, we'll see. Come back to this. Let's minimize this. Let's do a quick dry run to understand how. I'm going to minimize this size so it will be easier to dry run. Okay. Now coming back to this. See what you are doing here is, let's understand the approach first before moving to the dry run. Our approach here is, I need to find those nodes. I need to find the deepest leaf nodes. What is the meaning of deepest leaf nodes? Leaf node means there has to be no children for that first part. Now, when you say deepest leaf nodes, in the case of deepest leaf node, what is going to happen is they have to be at the maximum depth. So two things are there. I need to find the leaf nodes which are at the maximum depth. So each node that I'm visiting, I should know which depth I am or which height I am. Only then I can find which one is the deepest one. Okay. That is why this count depth function, this is just a function which is storing a mapping of which node is at what level. That's all. Which node is at what level. Now, once you find left height and right height, both are same. It means if you find left hand and right hand both are same, in that case, you're going to find, okay, this is the deepest node that I have found. That deepest node both exist on the same height. So root will be the answer. If it is less than this, then I'm going to recur for the right one. If root right is less, I'm going to recur for left one. Now let's take an example. This tree I'm talking about, let me take this chat window somewhere else. This tree I'm talking about, the one on the left side. Okay. What do? You say left depth equal to count depth, root left, right depth equal to root right. Okay. It will keep on recurring till left. It will keep on recurring till right, this complete function until it reaches from 3, 6 here, 3, 1 here, until 2, until 7. It will keep on recurring like this. Okay. So it will get the left type. It will give you the left depth. It will give you the right depth. In that case, your left depth, which is this left subtree, that will come out more than right depth. This part all agree? This part all agree? When you recur on the root tree, this root tree I'm talking about, let's look at one more time. This is the left subtree. This is the right subtree. So after this recursion, it has stored at every node, whatever is the depth there. For example, 3 depth is going to be 0, since we are starting from 0. 5 is going to be 1. This is going to be 2. This is going to be 3. Okay. So left subtree depth will come out to be 3. This will be 1 and this will be 2. So after this, even if you print left and right, you'll be able to see this left part will be 3 and right part will be 2. So condition will be this. Left is 3, right is 2. Now what you're going to do is you're going to recur to left. Okay. Now what will happen? The moment you recur to left, 5 will become what? 5 will become what? 5 will become root. Now you're going to compare 6 and this. In that case, right tree will have the higher depth. Now it will recur to right. Finally, when it will recur to right, let me do it here again. Finally, it will recur to right. 2 will become your root. This will become your left. This will become your right. So this is root. Your left depth become 1, right depth become 1. Both become same. You're returning the root. You got the answer as 2. So from 2, 7, 4, this complete subtree will be returned. All clear? All clear? Okay. Cool, then let's clear the console. One of the best ways, if you want to dry run, one of the best ways, print the depth or print the root. Both will give you the right answer. Print the depth or print the root, both will give you the right answer. For example, this case, if you just want to check it out, just check it out like left depth is and just give a space. Right depth is whatever right depth. Such kind of debugging are always useful. So let's see a test case. What we have, this one is fine. Run the code on this test case. What are you finding? 3 and 2. Now look at the same thing which I told you. Coming to this, 3 times it is called. 3 times it is called means this is height 1, this is height 2, this is height 3. What is it telling you? First left subtree, this is height 3, and this is 1, and this is 2. So first time when it is recurring, it is giving me 3 and 2. Same thing which I told you. Second time which is recurring, it will move to the left. Now it will say, let's clear this. It will recur to the left. It will say this height is 1, this height is 1, and this height is 2. Now when it moved to 5 as a root, now it is printing 1 and 2. So left depth is 1, right depth is 2. So since right depth is more, now finally it will move to 2. This will become root. Left depth will become 1, right depth will become 1. Same thing which I told in the diagram. You can see in the output as well. Everybody clear now? Everybody clear now? So whenever such kind of things you are not able to understand, just put debugging statement, that will be helpful. So right that, fine, let's run, let's submit. Anyhow, it's a debugging statement, not going to change any answer at all. Cool. Let's take this code. Let's move to Sublime. This is what we have done. Cool. Okay. Cool, guys. I think we are done with trees. All the good questions, not the good question, pretty much all the questions of trees we have done. Okay. Whatever are important from interview, non-interview perspective. We can do it without using map. I still don't get why map. Map is used to storing the result. So left tap, right tap, this 1 plus max. Max step root left, max step root right. What we're doing here is maximum depth we are calculating by root equal to null, 1 plus max. Yeah, same thing. You can do it by without map also. So the way I have used map is I'm maintaining which particular value is at which depth, which particular node is at which depth. That's why I'm comparing left and right height. But I agree, you can do it with pair also, or you can do it without pair or map also. Okay. If you're just calculating the height and you're comparing left and right height, you can do that as well. Okay. Cool. Now coming to this. What is the standard here? Yeah. All of this question we are done. So let's mark them as done.